Hello, I am Dr. Ozan Aktas from University of Southampton. I will talk about laser writing of graded index optical waveguides by phase segregation in initial homogeneous silicon germanium thin films epitaxially grown on silicon substrates. Here is the outline of my talk. First, I will start explaining our motivation for this work and give a brief literature review about the current methods to fabricate silicon germanium waveguides on silicon platforms. Then I will show our results for direct laser writing of silicon germanium waveguides by phase segregation at different constant scan speeds. To give you a better insight for the laser-driven phase segregation, I will also discuss the results of our simulations. Later I will talk about material and optical characterizations of the laser-written silicon germanium waveguides, and I will conclude my talk. Silicon germanium is a compound semiconductor. Its optical and electronical properties such as refractive index, mobility, electronic band gap can be tuned through the composition by changing the germanium fraction. To date, silicon germanium alloys have been extensively used in various fields for different applications. For example, heterojunction bipolar transistors in electronics, photodetectors, solar cells, thermoelectric generators in thermophotovoltaics, X-ray collimators in synchrotron optics. Last but not least, silicon germanium alloys are also promising materials for quantum cascade lasers, mid-air optical waveguides, optical interconnects, and many other applications in photonics and nonlinear optics. As silicon germanium is a CMOS-compatible material, it can be used as an integration platform for the convergence of electronics and photonics, where various components can be produced on chip, as illustrated in the figure. Silicon germanium waveguides have recently received interest for mid-air applications in integrated photonics due to low optical losses between 1 and 2 dB per centimeter in the wavelength range of 2 and 8 micron, and their optical properties tunable via compositional engineering. Fabrication of waveguides in silicon germanium alloys can be accomplished in several ways. The first example is the fabrication of graded index silicon germanium waveguides within bulk silicon wafers. Here, the waveguides are produced by using furnace annealing to infuse germanium from a germanium-rich strip source deposited on the substrate surface. Although optical losses less than 0.5 dB per centimeter were demonstrated at telecom wavelengths, this approach hasn't been widely adopted because of long process times over 6 hours at 1200 degrees Celsius required by the furnace annealing, which renders the fabrication of waveguides impractical. Germanium ion implementation is another method as it is most compatible and isoelectronic to silicon. Germanium implanted silicon has a refractive index of 3.96 due to the amorphization. However, the propagation loss of the implanted waveguides is around 30 dB per millimeter at telecom wavelengths, which is quite high compared to those of conventional waveguides. Last but not least, epitaxial growth of silicon germanium on silicon and subsequent lithographical patterning can be used to fabricate waveguides. Furthermore, graded composition can be achieved by modulating the precursors during the growth process. However, these graded index silicon germanium waveguides directly fabricated by epitaxial growth have two drawbacks. First, the graded refractive index can only be obtained in the growth direction, perpendicular to the substrate surface, and a step index profile in the plane for mode confinement still requires patterning of the surface, similar to the SiGe waveguides. Second, waveguides with the different graded profiles on the same substrate requires different growth processes for each of them, increasing the cost and complexity of the fabrication. In this talk, I will present another approach to fabricate graded index silicon germanium waveguides. The proposed mechanism is based on compositional segregation of silicon and germanium as opposed to the diffusion process. Recently, we systematically investigated laser-driven phase segregation in amorphous silicon germanium thin films. The laser writing setup and compositional redistribution can be seen in the schematic. On the right, the optical microscope image shows the two 7-micron wide silicon germanium microstripes laser-written at scan speeds of 1 and 10 mm per second. The difference in the color contrast reveals the scan speed dependent germanium redistribution on the top surface. To better understand the laser-driven phase segregation process, we did numerical simulations by solving the thermal transport equation and a segregation diffusion equation concurrently in COMSOL multiphysics. As can be seen from the temperature distribution given in the figure A, a maximum temperature of 1600 degrees Celsius is reached at the center of the laser exposed region at a power of 250 mW. It creates a molten zone traveling at the scan speed. The phase segregation occurs at the liquid-solid interface. The animation of the laser-driven phase segregation in a silicon germanium thin film on a silicon substrate shows the spatial and temporal evolution of the germanium mole fraction at a laser scan speed of 0.1 mm per second. Initial germanium fraction is 60% and homogeneous in the total volume of the film. Only half of the simulation domain is shown here due to the mirror symmetry. Laser-induced molten zone, shown in red color, travels along the scan direction, dragging the germanium-rich liquid, which solidifies at the trailing edge. After a silicon-rich transient, given in cyan color, a steady-state region emerges with a germanium-rich strip core and a silicon-rich undercladding. Complete mixing results in homogeneous distribution of germanium in the molten zone. On the other hand, in the case where the scan speed is higher, such as 100 mm per second, a build-up of the germanium, given in the dark red color, occurs at the trailing edge of the molten zone because of insufficient diffusion-limited germanium transport. After a very short silicon-rich transient, a steady state, which can be indefinitely long, quickly emerges. This is the schematic of our experimental setup used for laser processing of silicon germanium epilayers. The thermal source is a laser emitting continuous wave radiation at a wavelength of 532 nanometers. To avoid distortion in the laser beam, we adjusted optical power by using a polarization beam splitter and a half plate. Laser beam was focused on the top surface of the epitaxially grown silicon germanium thin film using a 10x objective lens to produce a spot size of 5 micron in diameter. A dichroic mirror was used to couple a collimated white light source into the optical path. CCD camera allows for in-situ monitoring of the surface during the laser processing. Samples were mounted with a vacuum holder on software-controlled motorized stages, which are capable of precision movements in 3 dimensions. These stages were used to scan the sample under the laser beam at scan speeds ranging from 0.1 to 200 mm per second. The power was adjusted between 1 to 3 watts. High temperatures sufficient to melt the semiconductor alloy epilayer can be reached due to the high optical absorption of silicon germanium in the visible spectrum. The diameter of the molten zone can be smaller or larger than the spot size depending on the laser power. We begin our experimental work by applying laser processing to homogeneous silicon germanium epilayers with a thickness of 575 nanometer and a germanium concentration of 50%. The silicon germanium epilayers were epitaxially grown on silicon substrates by reduced pressure chemical vapor deposition. Laser processing was conducted at the same power with different constant scan speeds in the range of 0.1 to 200 mm per second. Depending on the scan speed, laser-driven liquid-solid interface produces microstripes solidified with varying germanium compositions on the top surface, as shown in the optical microscope image in figure A. The laser-written silicon germanium microstripes for the low scan speeds of 0.1 and 1 mm per second are barely distinguishable. However, wider microstripes emerge with a yellowish color as the scan speed increases and germanium accumulates on the surface. We then carried out 3D finite element method-based non-isothermal phase field simulations to compare with the experimental results. To understand the effect of the thermocoupled convection on the distribution of composition within the molten zone, Navier-Stokes equations were also solved. To reduce the simulation volume and computational cost, we choose a beam spot size of 2 micron in diameter and a scan range of 10 micron, which are smaller in size compared to the experimental parameters. Simulation results presented in figure B show the spatial redistribution of the germanium mole fraction within the laser-processed microstripes at various constant scan speeds. Phase field modeling provides good qualitative agreement when compared to the experimental observations. For example, both experimental data in figure A and the simulation results given in figure B show that the widening of the germanium-rich strip core on the top surface occurs as the scan speed increases. For further qualitative comparison of our simulations result with the experiments, a laser-processed silicon germanium epilayer was cleaved in the middle, and its cleaved edge was polished at an angle to reveal the cross-section of a waveguide laser-written at a scan speed of 200 mm per second. The simulated redistribution of the composition on the top surface and in the cross-section shown in the figure C agrees well with the experimental result shown in the optical microscope image in figure D, displaying similar features. The germanium-rich top surface and boundary of the silicon-rich cladding are clearly observable via natural color contrast. Germanium profiles calculated by the phase field simulations along different directions at the top surface and cross-section are shown in the figure A to C for the silicon germanium waveguides laser written at different scan speeds. The increase of the germanium content in the stagnant layer close to the liquid-solid interface can be clearly seen in figure A. A maximum germanium mole fraction up to 0.7 mole is reached on the top surface in the solidified region for the scan speed of 200 mm per second. Higher scan speeds result in leveling of the germanium composition, widening the width of the germanium-rich strip core as shown in the figure B for the scan speed of 500 mm per second. The most silicon-rich region in the undercladding occurs at the bottom close to the silicon-germanium-silicon interface as shown in figure C. The effect of laser-driven phase segregation on the dispersion of the initial germanium mole fraction can be clearly seen by calculating the histograms of the composition within the entire solidified volume in this steady state region for different scan speeds as shown in the figure D. These results complement our understanding of the formation of graded index waveguides using laser processing. To conduct a quantitative comparison, the cross-section of a silicon germanium microstripe, laser written at a scan speed of 200 mm per second, was analyzed using scanning tunneling electron microscopy with energy dispersive X-ray spectroscopy. The high-angle annular dark field image shows the material contrast in figure A due to the redistribution of the composition in the melted region, as given by the EDX map in figure B. Our simulated result in this figure was calculated neglecting the thermocoupleur convection, but using the actual experimental thickness of the silicon germanium epilayer and the width of the laser written stripe. Figure C shows the simulated silicon germanium composition at the cross-section, revealing the 2D spatial redistribution of germanium in the germanium-rich core and silicon-rich cladding. The one-dimensional depth profile of the germanium concentration was also calculated and compared with the EDX data in figure D. Simulated two-dimensional and one-dimensional germanium profiles agree quantitatively well with the experimental data measured by EDX, which has an error margin of ±5%. The schematic is showing our experimental setup used for coupling of light into the laser-written silicon germanium waveguides. As a light source, we used a CW fiber laser emitting at a wavelength of 2 micron with a maximum power of 15 mW. The sample used in the experimental consisted of a series of graded index silicon germanium waveguides laser-written at different constant scan speeds in the range of 0.1 to 200 mm per second. To prepare the facets for the optical coupling, both ends were cleaned and inspected using a microscope for flatness. The sample was then placed on a 3-axis high-precision stages. TM and TE polarized light were free space coupled in and out of each waveguide by using 60x and 40x microscope objectives respectively. Careful monitoring of the input and output coupling using infrared cameras allows for efficient coupling into the fundamental mode. The light from the output faces was collimated and the mode profiles were captured by the IR camera. Germanium distribution at the cross-section of a laser-written silicon germanium waveguide, which was obtained by a phase field simulation, is given in figure A. The corresponding refractive index profile, which includes the photoelastic effects, is shown in figure B. The simulated fundamental mode profiles for the TE and TM polarized light at a wavelength of 2 micron are shown in the figures C and D respectively. For a proof of principle experimental demonstration, we used a 1 cm long silicon germanium waveguide that was written at a scan speed of 200 mm per second. The light at the output was collimated by a 40x objective and imaged by an infrared camera, which captured the image of the TE and TM polarized modes shown in the figures E and F respectively. In agreement with the optical simulations, we observed that only fundamental modes were guided through the laser-written silicon germanium waveguides at a wavelength of 2 micron. Moreover, optical guiding was observed even for the waveguide written at the lowest scan speed of 0.1 mm per second, where the least compositional separation of silicon and germanium occurs within the laser processed region. Therefore, we incorporated the photoelastic effects, which are strain-induced changes in refractive index. We found that an increase of 3% in the refractive index within the laser processed strain region gives the best agreement with the optical experiments in terms of matching the mode profiles. This observation confirms our assumption that residual tensile strains increase the refractive index in the laser processed regions to allow for optical guiding. TM polarized mode was found to be lossy for this thickness. However, more confinement can be provided for the TM polarized mode to achieve optical guiding at much longer wavelengths by using thicker silicon germanium films and higher optical powers. As a future work, we will investigate formation of in-plane transverse silicon germanium superlattices within waveguides by modulation of the laser power or beam position during laser processing. The animation shows the spatial and temporal evolution of germanium molar fraction due to the sawtooth modulation of the laser beam position back and forth while laser processing on a silicon germanium epilayer at a constant state scan speed of 25 mm per second. The initial germanium composition is 0.5 mol within the entire volume of the silicon germanium epilayer. Modulation of the beam position back and forth results in an in-plane transverse superlattice with interfaces in the morphology of the laser beam. Total length of the superlattice is determined only by the scan range. These could be indefinitely long. The lateral size is determined by the laser spot size. As shown in figure A, a 10-period Bragg grating with a pitch size of 300 nm was chosen for the wavelength filtering application at a wavelength range around 2 micron. Total length of the Bragg grating was kept short due to the computational constraints for the optical simulations in 3D. However, to increase the coupling between the propagating and counter-propagating optical modes in such a short waveguide Bragg grating, we ensured that maximum refractory index modulation was achieved in the periodic composition profile as shown in figure B. The calculated transmission and reflection spectra of the 10-period waveguide Bragg grating are also shown in figure C. As a conclusion, I would like to stress on the contribution of our work and its implications. We conducted 3D finite element method-based non-isothermal phase field simulations to investigate solidification of silicon germanium epilayers during laser processing, incorporating laser-induced thermocapillary convection. For the first time, we demonstrated laser-driven phase segregation in silicon germanium thin films epitaxially grown on planar silicon substrates. It enables on-chip post-deposition local tailoring of composition in silicon germanium thin films, which can be used to produce graded index waveguides with tunable compositional profiles. Our method can also be applied to study the binary alloys of ternary semiconductors such as aluminium gallium arsenide, metals such as nickel copper, ceramics and organic compounds which have phase diagrams similar to that of silicon germanium alloys. Finally, our phase field simulations revealed that various in-plane heterostructures and superlattices can be fabricated within waveguides by controlling the phase segregation through modulation of the scan speed, power and beam position. This is the end of my talk. Thank you very much for your time and attention. If you have any question, I would be happy to answer it.